On page 72, title it Multiplying and Dividing Radical Expressions. So we got done with adding and subtracting them, and now we're going to learn how to multiply and divide them. So the rule from your Algebra 1 days that said that the square root of a times the square root of b is equal to the square root of a times b inside one radical works for any index regardless of what it is. So the same thing is true for dividing. We have that same rule as well that you've already seen in Algebra 1. So now we're going to apply this rule. So when you have two or more, that we're going to multiply or divide for our radical expressions. So the directions say to simplify the expressions, assume all variables are positive. The reason it says that is because if you have, for example, the square root of a -2, that's bad. So our a and our b are always going to be positive, so we don't have to worry about taking the nth root of a negative number. And we don't have to worry about that. All right, so for number 1, we have the cube root of x times y times the cube root of 7x. Notice this time only the index has to match. When we were adding and subtracting radical expressions, we had to make sure that the radicands also match. But this time we don't. We only have to make sure that the index matches. So for this one, you can make it into one big cube root. You can multiply 7x times xy and get 7x squared y for your radicand. So that becomes our answer, and you're done. The reason you're done is because you can't take the cube of 7 or x squared or y, so you can't simplify this any further. For number 2, we have 2 times the square root of 3z times the square root of 6xy cubed. So since both of these have a square root, we're going to go ahead and multiply the 6 and the 3, the x with the x, and the y cubed with the z. When you do that, you end up with 18x squared y cubed times z. Now, 18 is not a perfect square, but it has one inside of it, and that one is going to be 9. So that when you break that up, you get 2 times 9 for your 18. And then y cubed is not a perfect square, but it does have one inside of it. That would be y squared. So I can break that up into y squared times y, because when you multiply that together, you get back y cubes. And now, when you take the square root of the things that are allowed to come out, that 9 will turn into a 3, and multiply by this 2 to become 6. The y squared and the x squared both, when you take the square root, become xy, so they'll come out of the radical. And then the y and the z will remain along with the 2. So the final answer for this one is 6xy, I'm sorry, there should be a 6 right here. It would be 6xy times the square root of 2yz, and that's your final answer, because it can't be square rooted any further. Now, for number 3, we've got the 4th root of 8x cubed times y squared. We want to multiply that by the 4th root of 8x to the 5th times y cubed. Same thing, we'll multiply 8 times 8 to get 64. We'll multiply x cubed times x to the 5th to get x to the 8th. And we'll multiply y squared times y cubed to get y to the 5th. And the reason we can do this is because you have an index of 4 that's the same thing. If these indexes were different, then you would not be able to do this. Now, the 4th root of 64, we know what that is. We'll know what the 4th root of x to the 8th is. This y to the 5th isn't a perfect 4th root, but it does have one inside of it, which is y to the 4th. So what I'm going to do is I'm actually going to break that up into y to the 4th times y. And now I'm going to take the 4th root of these individually. The 4th root of 64 is 2. The 4th root of x to the 8th is x squared, because when you multiply x squared by itself 4 times, you get x to the 8th. The 4th root of y to the 4th is y, and we're left with just simply the 4th root of 4 times y. Oh no, I did this wrong. I'm so sorry. Okay, so the 4th root of 64 is not 2. It has a perfect 4th root in it. That is 2 times 2 is 4 times 2 is 8 times 2 is 16. Okay, my bad. So this is actually going to be broken up into 16 times 4, so that's my fault. The 64 does not have a perfect 4th root. It's actually written as 16 times 4. This is my fault. So now the 4th root of 16 is 2, but that's why there's still a 4 sitting here. So we really should have broken this up into 16 times 4 right here, which would make this the 4, and that's why it remained inside, and that's why there became a 2 on the outside. That's my bad. So rewrite this third line right here as a 16 times 4 instead. My bad. And then this becomes your final answer. For example 4, we have a division of two radicals, and so we've got the square root of 16x to the fifth times y to the fourth divided by the square root of 2xy. We can make this into one big square root since they both have the same index of 2, and so when I do that, this is my new expression under the radical. Now, 16 divided by 2 is 8, x to the fifth divided by x is x to the fourth, and y to the fourth divided by y is y cubed. When you take the square root, 8 itself is not a perfect square, but it has one inside of it, which is 4. And then x to the fourth also is not a, y cubed is also not a perfect square, but it does have y squared in it. So I'm going to rewrite that as 4 times 2 for my 8, leave x to the fourth alone, but rewrite y cubed as y squared times y. So when I go to take the square root of each of these individually, the square root of 4 is 2, which comes to the outside, leaving the 2 on the inside because it's not a perfect square. The square root of x to the fourth is x squared, the square root of y squared is y, and then the y is going to remain because it's not a perfect square. And then final example number 5. We're going to take this expression and make it one big cube root instead. And so when you do that, you get this under the radical as your new radicand. 54 divided by 16 is going to be reduced. We can divide both of those by 2, and so that becomes 27 over 8. A cubed divided by a squared is going to be just a, and then b to the fifth divided by b squared is b cubed. And that still has the cube root on the outside once I reduce it. Now, this is kind of weird, but I can actually go back and put the cube root back at the bottom because 8 is a perfect cube. So I went ahead and put it back as 2 separate cube roots like it was at the very beginning. And again, that was because this 8 is now a perfect cube. So when you do this, the cube root of 27 becomes 3. The cube root of b cubed becomes b. But then the cube root of a can't be simplified, so you'll leave it there. And the cube root of 8 is 2. And that is your final answer. And that is it for this page.